Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to continue our series on equilibrium problems. This is going to be problem number 3, and these vary in levels of difficulty. So as we continue, the problems get a little bit more challenging. Okay, so right now we're going to be working on question number 3. So if you want to pause the video, write the prompt for question number 3. When you come back, we'll be working on the problem. Okay, so once again, we have a problem where the prompt is giving us things of moles of hydrogen and moles of iodine, okay? And what we need to do is we need to put that in the molarity units, because when we're using the ice chart, it either has to be in a molarity unit or a pressure unit, okay? So when we stick that in into the calculator, the moles divided by the volume being a 5-liter container, we're going to get the molarity of the hydrogen as 0.001 molarity, and that's one of our givens, okay? And the iodine is going to be 0.002 molarity. And it doesn't tell us anything about the hydroiodic acid, okay? But when we read this, it tells us one of the equilibrium positions. It does give us the equilibrium position of the hydroiodic acid, and it's giving it to us in scientific notation, okay, which makes this problem for some students a little bit more challenging because they need to be able to enter these numbers in your calculator correctly. And believe it or not, okay, taking a problem that's in standard notation for numbers into scientific notation gives some students problems. The other thing that you're going to notice is that we're no longer talking about A, B, C, and D for our reactants and products. We're actually using real chemicals here in problem number 3, okay? So the problem works exactly the same way as the other two, okay? It's just with more challenging numbers. So the question again is going to be, what is the equilibrium constant equal to? So we're going to take a look at the hydroiodic acid. We know that it starts at 0 and it jumps up to 1.87 times 10 to the negative 3. So we know that this is going up 1.87 times 10 to the negative 3 molarity. And if we know the change of one of them, we can figure out the change of all of them. Okay, so we're going to take this 1.87 times 10 to the negative 3 molarity of HI, and we're going to do a train trap to go from molarity of HI to molarity of either the hydrogen or the iodine. Okay, we'll go to iodine first. Okay, and it ends up being a 2-to-1 ratio. It's going to end up being a 2-to-1 ratio for this one and a 2-to-1 ratio for this one. So we're going to get the same numbers here and here. So if I take this 1.87 times 10 to the negative 3 and divide it by 2, we're going to find the change for both the iodine and the hydrogen. Okay, and when we do that, this is going to go down. Remember, reactants react, so they're going to be consumed. So it's going to be 9.35 times 10 to the negative 4. And that's going to be for both of them, because both of them are 2-to-1 ratio. Both of them are. Okay, so we now know the change of everything, and if we know the change of everything, we could do some simple subtraction to figure out their equilibrium position. So 0.001 minus this number is going to give me 6.5 times 10 to the negative 5. Okay, and if I take 0.002 and subtract it by this number, I get 1.065 times 10 to the negative 3. Okay, so once again, we got some challenging numbers to work with. Okay, but at the end of the day, this is all going to be the same concept. We're just going to plug this information into our equilibrium expression, which is the products over the reactants. Okay, so this is going to be HI over H2 and I2. Okay, now remember, the coefficients are the exponents. So we have an exponent on the HI. So we're going to plug in these values. So HI is 1.87 times 10 to the negative 3, and we're squaring that. And then we're going to take 6.5 times 10 to the negative 5, and 1.065 times 10 to the negative 3. And when we plug all of this into our calculator, we get the number of 50.5 for the K sub C value. I hope you got that number. Okay, if you did and you found this problem easy, go ahead and continue on in our video series of equilibrium problems. And if you found this content helpful, please give it a like and subscribe. And when you leave a comment, it pushes this information out to other students that are interested in learning chemistry.